Right. So let's go to the spec. Sometimes LTAC almost looks like ASCII art. Just, yeah, it comes out that way. Let's find this. Right. Right. So, here's what we ultimately want to prove. Right. I want to show that if I have a single node, I want to show that when I run the primary backup system in the asynchronous network, that nothing sort of extra happens, right? So what this says is, suppose that I could produce some trace, the primary backup system could produce some trace in the asynchronous semantics. What I want to know is that the underlying system could have done the same thing, itself, right? So I haven't added anything extra in a sense. Now here's that trick, right? Remember on the slide we said that we have this sort of lift of a property. So we have this revert. We have these revert things like revert state and revert trace, right? And those are mappings from things going on for the underlying system. So mappings from our state to what we consider the analog, right? Like at this point in the adversarial semantics, when we're simulating this system design for a friendly semantics, what do we think its state would have been in the ideal semantics, right? We're trying to simulate this system where there are more kinds of faults. So like, what do we think its state would have been, right? So that's the way we lift. It's sort of, what we think it should be in, right? That gives the analog of the properties that we have. Okay. Yeah, just a lot of lemmas and grinding. Yeah, and then there's some helpers. So yeah, and there's also a bunch of different flavors of that point. But okay, so this is our sort of first more real verified distributed system transformer. Primary backup is something that people actually do in practice. People actually have gotten wrong, even though it's simple. And we can actually prove this in just 1,300 lines. So yeah. So let's look at another example, which is a lock server. This is another kind of thing that you want to make sure you get right when you're building systems, right? So basically what we want to do is we want to be able to have some server and a bunch of clients. We want to guarantee mutual exclusion between the clients. So I want to know that at most one client at any time holds the lock. And this is useful because external clients can draw conclusions about the state of other nodes in the system, right? And so this is this kind of, again, this thing we said earlier about you're trying to have shared knowledge across the system even when failures and faults are happening, right? So we want to be able to safely conclude what's going on at other places, even though nodes might be failing and messages might be getting dropped, et cetera, et cetera. So here we're going to have something a little bit different. So here this is not a transformer, it's just a flat system we're defining. But it does have a parameter, which is the number of clients, right? So when we verify this, we're going to quantify over the number of clients in the system. And there's only one server, right? And what that means, though, is that we're going to get a proof that holds for sort of any topology, right? So for any configuration, rather. So no matter how many clients I have, I'm going to know that I still get this mutual exclusion property. And I can use this for all different sizes of systems. And this works basically the way you expect. So if the client is told that it got the lock, right, from the server, it's going to set its state to true, and it's going to tell its external client. So this is a little bit confusing. right? Because remember we said clients use sort of black boxes that are out in the world. They send us inputs. We send them back outputs. So here we have a thing called client. This is actually a node named client, which is perhaps confusing, but hopefully it doesn't throw anybody too much for a loop. So when clients are told they have the lock, they set their state accordingly, and they inform the external client that they now have the lock. When a client is told, let's see, where is that? When a client is told that their external client is done with the lock, as long as they currently have the lock, they set it to, they release it and they notify the server that they're giving up the lock, right? And then the server sort of coordinates between the clients. So basically, it keeps a queue of current requests, right? So somebody might get a request from their external client to get the lock, but some other client has it. So, they're going to ask the server for it. If somebody else already has the lock, then what we're going to do is we're going to add that request to the queue. And whenever somebody tells us that they're giving up the lock, then what we're going to do is we're going to see if anybody else is waiting on it. If somebody is waiting on it, we will update our state, we'll update the queue, we'll update who's holding the lock, and we'll tell that client that they now have the lock, right, the one who is next in line for it. Otherwise, we don't need to do anything. Nobody's waiting on it. Hopefully this is convincing, right? This is sort of what you'd imagine a lock server does. And then, we start grinding. And there's a bunch of lemmas. And if you go through it, Eve doesn't like the grinding. Oh, there's a no.
Oh, no problem.
At the end of the day, you get this nice mutual exclusion property. So let's find that. Right. So what we're going to be able to prove is that in every reachable state, at most one client holds the lock at any time. And we're going to have a few different flavors of this, right? We have like the prime version of it. Because for different use cases, for different ways we might want to wrap this system, there's different flavors we want of it. So, but we always, end up with this property that any possible state we can reach, at most one client has the lock at any time, right? And so we know that's true. Now, this is designed for a system where messages aren't dropped, right? This corresponds to like our shuffle semantics. So what might go wrong if we go to the duplicate semantics or to the drop semantics for our lock server? Right? So how does this work again, right? You got a bunch of clients, you got a server. The client nodes are somebody in the outside world says, hey, I want the lock. They ask the server, can I have the lock? The server either comes back, it either puts it on the queue or it says like, yeah, you can have it. If they put it on the queue, there's somebody else who has the lock. When that person's done, they'll release it from the server, and eventually you'll get your turn, right? That's all the system does. So now imagine we're in a network where messages can be duplicated. Can anybody think of a thing that might go wrong if you can duplicate messages for this system?
So a client could request the lock, get the lock, release the lock, and then get a duplicate of the lock granting message. Yeah,
that's exactly right. That's exactly right. Does everybody understand that? So suppose that the server has ever granted you a lock. If that message got duplicated, it could be delivered again at some arbitrary point in the future, right? So you might just get told out of nowhere like, oh, you have the lock now, by the way. And you're going to think, well, look, the only time the server sends me a lock message is when I asked for it. So because I got this lock message from the server, I must have asked for it. I better tell the external client that they have the lock now, right? And now the external node, like whoever, the external person you're talking to, all of a sudden they think that they're the only person with the lock, but in fact somebody else has it, right? And so we've totally destroyed this property that we went to all this trouble, a bunch of listy lemmas to prove. Will be completely obliterated. So to handle that, we want to be able to detect duplicates and avoid destroying the whole point of building these verified systems in the first place. We want to be able to run in these sort of more adversarial semantics. And so we have sequence numbering, right? So this is the Verity version of the bit we saw before. Oh yeah. This one's definitely right because I proved this. So yeah, I'm not worried about it on this one. This one I feel confident about because if it's wrong, cock is unsound. And I don't think that's going to happen. Okay, so we have the same thing with sequence numbering, right? We have some transform data. TD num is kind of like our fresh. We have some set of scene stuff. Oh, I see. What we can do is we can use that to track ourselves as well. Oh, that doesn't quite work either. But anyways, right, so we have some fresh, we have some scene, and we have the data for the underlying system, right? So again, the whole game here is we're trying to simulate some other distributed system as if it was in a nicer semantics, and we're going to do it in a way that we can handle the faults. Yeah, this is just, yeah. Okay, I didn't totally screw up. This is the same. And it works just like the handlers on seqnum, right? When we send a message, so here it's not done with an action in the monad, but when we want to send a bunch of packets from the underlying system in the wrapped system, what are we going to do? Well, if there's no packets, you don't got to do anything. You're done. Otherwise, what you're going to do is there's some packet, you need to wrap it. So you're going to send it to the same place it was already destined to. And then you're going to add a sequence number to it, right? And that's it. So this is just like what we saw in Simple DS. Now the difference with Simple DS is that when you go to the file of the same name with correct on the end, this doesn't just say mini project, right? In fact, there's instead like 1,000 lines building up to this proof, which is that anything that is true about the underlying, anything that's true about the system in async, let me get this right, is also true in dupe. Right, and so here's sort of, there's a ton of lemmas that build up to this stuff. But there's this pattern that you'll see over and over, right? And you also see this in, like when you do compiler verification, is you see sort of a simulation diagram, right? So we want to know that if we have something that's true, like we were reachable, for example, and we take a step, that some other things will continue to be true. In particular, this has to do with lifting back up the state of the system that we're simulating, back to a higher level. Okay. So if you go do the sort of in Simple DS seqnum, there's a couple of invariants that are suggested that are a lot easier than doing all of this work. Right? This is quite a lot of grinding. But if you do want to try to do the full thing, I would encourage you to look at the invariants that are approved here, and also some of the tricks with tactics. You might notice yesterday and today there's some tactics that are not super standard. There's this struct-tech library that we'll talk more about tomorrow when we talk about how we scaled this up to proving raft correct. I think those were the main things I wanted to do. The other thing that's in the README for tomorrow is to actually run the system. So there's, in this last one we talk about, last couple things, right? We talk about actually running the code. So if you want to do that, I just wanted to be really clear about something. So in here, there is this, so this is in the DeepSpec repo. There is this Verity runtime copy. And I put that in there because one of the things that I wanted people to do is actually go look at the shim code, right? So remember this stuff about like, hey, the semantics assumes handlers are atomic. The OCaml code you write that actually does stuff on the network should do its best to make that true. So one of the exercises is to go look in here and do that. I would not encourage you, though, when you try to actually build the executable lockserve, which you should do from the Verity lockserve directory, to try to build it from this version. You should really use OPAM. It'll make your life a lot easier. But yeah, so I think those were really the big things I wanted to get through today. So what did we do? We moved from just defining semantics and systems, improving systems, to also defining transformers, right? And what's the transformer do? Well, it abstracts out this mechanism for handling faults. And what's cool, right, is that it actually composes. So you can build stacks of these, right? If you have semantics that each add sort of another kind of fault, and you have system transformers that know how to take a system that can't handle that fault and add fault tolerance so that it does, you can stack these up. You can layer these transformers, and it's this sort of nice modular way of abstracting out reasoning about fault tolerance. So not only do you get to separate reasoning about application and reasoning about faults, but even when you're reasoning about faults, you can break that up into smaller parts that you can stick back together, right? You can reason out sort of one kind of fault at a time. And so that's really, honestly, that's sort of the main punchline from Verity, is that here's a modular way to do fault tolerance in distributed systems that you can verify, right? You can sort of stack these up and build stuff. Now, tomorrow we'll talk about some of the things you can't do in Verity. There are other dimensions of modularity you don't get because of the way clients are defined in other things. And so, we'll talk very briefly about that. I heard that there's a separation logic fan club at 2 or something. So if people are going to talk about Iris, you also might want to think about Diesel there, which has this sort of trying to support these other kinds of compositionality. But yeah, okay, any questions? People okay with Verity? I feel kind of bad, right? Like, I understand these buffers are just like, okay, here's a wall of LTAC. Good luck, right? I don't know what to tell you guys. I think that right now that's kind of the reality. When you build these big systems, there's just a lot of grinding that goes into it. But the thing to keep in mind, right, is that, I don't know if you guys remember, so I remember one of the very first research papers I ever read was the CONCERT paper, right? And people just flat out never thought that would happen. 10 years ago, 12 years ago, people never believed you would verify a C compiler, right? It just completely changed the way people thought about stuff. And then what they said was yeah, but compilers, PL people know a lot about compilers, and functional programming is good for implementing compilers. Of course they could verify a compiler, right? Of course they could. And then the Cell4 people came out, right? And they verified an operating system, which was incredible, right? This is super exciting. This is like core infrastructure. You have an OS kernel and you have a compiler, right? Like, we're really getting somewhere. This is awesome. But then people said, yeah, but it's a microkernel, right? Like, the interrupts don't work right, Like, it'll never, do anything. And then, one of the things that I did, right, it's a little piece for my PhD, I formally verified a web browser kernel, right? And I was excited. It's like, look, here's a verified web browser. When you run this thing, you get actual security guarantees, right? And web browser's like 1 million lines of code. Oh, sorry, I didn't set that one up right. The complaint before that was people like, yeah, but these things are all like a few thousand lines, right? Nobody will ever verify like a system that's actually like 1 million lines. And so, I for my PhD thesis, I verified a browser kernel, right? And you actually got guarantees about all 1 million lines, right? So as long as you have isolation, you can actually use Coq to prove things about the behavior of that whole system, right? You know that the JPEG decoder isn't going to leak your credit card or whatever, right? You can get these guarantees about what happens. But then people said, yeah, but you just did it for the kernel part, right? Like, whatever. And then people said, yeah, but okay, but all these big actual systems, they're all sequential, right? Nobody's dealing with concurrency or false or whatever, right?